Okay, today we want to look at polygons. Now last time we looked at triangles, which were a special kind of polygon. We'll do a little bit more rigorous definition of polygon today than we did yesterday, since this is actually about polygons. But so a polygon, so yesterday remember we talked about it being a closed figure, and we'll add, so is a closed and then plane figure, so it all has to lie flat in one plane. It can't be in multiple planes, so it all has to fit into one plane. So it's a closed plane figure formed by 3 or more line segments. Okay, so that is the definition of a polygon. So it's closed, it's a plane figure, and it's formed by line segments. Okay, so a couple of characteristics. Okay, so each segment will intersect exactly 2 other segments, and only at their endpoints. Okay, and no 2 segments with a common endpoint are collinear. Okay, so that just gives us some more exact ideas about how we can draw these things. So imagine, okay, I've got a figure, let's say like this. Okay, so notice it's closed. That means, okay, so this right here, each segment intersects exactly 2 other segments only at their endpoints. This will guarantee that it's closed. So if I look at a segment, here's a segment. It intersects exactly 2 other segments. So segment AB intersects BC, and it also intersects A, B, C, D, E, F, and it also intersects AF. So AB only intersects 2 other segments, exactly 2 other segments, BC and AF. And when they intersect, it's only at their endpoints. Okay, so they don't cross each other somewhere off of, off in the middle someplace. So just only at their endpoints. Okay. And then this part, no 2 segments with a common endpoint are collinear. That just says, I'm not going to have, a straight line and call that ABC and call that 2 different sides. It would just be one side. So I can't have, so anytime that I have 2 different segments, they can't be all in the same line. They have to be 2 separate sides. Okay, so we have something that looks like this, and then the endpoints of all the segments are called vertices, just like in a triangle. So all of these are vertices. Okay, and then all the segments are called sides. Okay, and as you can imagine, we would like to be able to classify polygons in a similar way that we classified triangles. We can classify them by how many sides they have and by some things about their angles as well. So let's look at how we might go about classifying polygons. Okay, so classifying polygons. Okay, so first of all, one of the ways that we do is by their number of sides. We'll probably make a list of that. So that's kind of long, so let me make a separate, first talk about angles. So we have something called equiangular. So an equiangular polygon, as you can imagine, is just like an equilateral triangle where all of the angles have the same measure, all the angles measures are equal. So all angle measures are equal. Okay, we also have something called an equilateral polygon. And equa and then lateral means side, so as you can get this, all the side lengths are equal. Okay, and then we have a really super special polygon called a regular polygon. And a polygon is only regular if it's both equiangular and equilateral. So it has to be both of those, not just one, but both of them. Okay, so let's look for an example. Let's say we had, okay, I'll do a pentagon. Let's see if I can try to draw it. So if all of these sides were exactly the same, so it's equilateral, and then all of these angles in here were exactly the same, so it's equilateral, equiangular, this would be regular. Okay, now we could have a different kind that where all the side lengths were the same, like this, where all of the side lengths are the same. But notice that the angles are not the same. We've got some right angles, some obtuse angles, and acute angle. This is, so it's not regular. This is called irregular. Okay, so even though all the side lengths are the same, the angles are not the same. Okay, so to be regular, it has to have both equiangular and equilateral. Okay. So irregular just means not regular. Okay, so when we classify polygons, we will want to classify them by the number of sides, and then as well as using words like equiangular, equilateral, regular, or irregular. Okay, so but the major way that we classify polygons is by the number of sides. So we'll look at the number of sides and then how we classify that. Okay, so we've already talked about 3 sides. That's called a triangle. Okay, if it's got 4 sides, what's it called? Okay, if you said rectangle, no. If you said square, no. If you said parallelogram, no. All those are types of 4-sided figures, but it's not the general name. 4-sided figures are called quadrilaterals. Okay, so quad is like 4, lateral sides, quadrilateral, 4 sides. Now, a square is a very special kind of quadrilateral. It's a regular quad because all of the sides are the same length and all the angles are exactly the same. So that would be a regular quadrilateral. Okay, but we don't call all 4-sided figures polygons, squares, or rectangles, or anything like that. They're just called quadrilaterals. All right, 5 sides. You probably know this one. This is a pentagon. And if you think about in Washington, D.C., we've got the Pentagon. It's a 5-sided building if you look at the aerial view of the Pentagon. That's why it's called that. And then 6 sides is a hexagon. Okay, so 6 sides is a hexagon. You got the X in there like 6, so that's easy to remember. Okay, then 7 sides. This one's really tricky. This is a heptagon. Hept with an H, not sept. Okay, so some people mix this up. It's not, it's a heptagon. Okay, if you're not familiar with this one or you forget this one, you might want to put a little star there. So 7 sides is a heptagon. Most people don't have trouble remembering 8 sides because they like the little creature that swims in the sea with 8 legs. That's called an octopus. So this is easy to remember that this is an octagon. Okay. And then they start getting tricky because you might not have used ones after this very much when you were younger. So these ones you're just going to have to memorize. So 9 sides is a nonagon. A nonagon. Okay. 10 sides is pretty easy. It's a decagon. Okay. And so that dec prefix you see a lot in the metric system, so like a decameter and that kind of thing, you've learned that before. So a decagon will have 10 sides. That one's fairly easy to remember. Then 11 sides is a hendecagon. A hendecagon. Okay. And then 12 sides is a dodecagon. Okay, so those are most of the ones that you will need to know. And yeah, so that looks good. Okay, the other thing that we use to classify polygons are the words convex and concave. Okay, and before we can talk about what convex and concave are, we have to talk about a diagonal, because those are defined in terms of a diagonal. So the diagonal of a polygon is a segment that connects two non-consecutive vertices. Of the polygon. So let me draw another polygon here. Okay, so if I were to look at this polygon, okay, A and B are consecutive vertices because they're right beside each other, and A and F are consecutive vertices because they are right beside each other. So a segment that connects A and B or A and F would not be called a diagonal because those are connecting consecutive vertices. A diagonal connects non-consecutive vertices. So A and C are examples of non-consecutive vertices. So if I were to draw this line segment, that would be a diagonal. Okay. Let's look at some other non-consecutive vertices. Let's see, what about B? B and F. That would also be a diagonal. Okay, so those are non-consecutive vertices. I could also do B to E or B to D. So you can see there's lots and lots of different diagonals in there. Okay, and so when we look at the words convex and concave, these are related to diagonals. Okay, so a polygon is classified as convex if, okay, no diagonal that contains exterior points can be drawn. And it's concave if there is at least one diagonal that contains exterior points. Okay, so let me draw you another example of a polygon here. Okay, so this polygon has 1, 2, 3, 4, 5, 6, 7, 8 sides. This is an octagon. Okay, it's definitely irregular. Okay, and now if we look at it, okay, we want to ask ourselves, is it convex or is it concave? Okay, so to determine that, I have to look at the diagonals. Now, can I draw any diagonals that would contain exterior points? So that would be points on the outside, of the figure. Okay, now here, if I take A and connect it to G, that's a diagonal. This is a diagonal that contains exterior points. So a diagonal that contains exterior points. Okay, so since this contains exterior points, this one will be concave. And if I want to show that something is concave, the way that I describe it as being concave is you would say, this is concave because there is a diagonal that contains exterior points. So when you're describing to me, don't say something like, oh, it caves in, or something like that's not a rigorous mathematical description. Okay, when you describe something that's concave, you need to say that there is a diagonal that contains exterior points. Now if we look at this one up here, okay, if I finished drawing in the diagonals, okay, well there's the diagonals from A. I drew all of the diagonals that go to A. Now the diagonals that go to B. I've drawn all the diagonals that go to B. And now, let's see, to C. Okay, I need to add these diagonals that go to C. And D, there's another diagonal in there that goes to D. Okay, I've got all the ones that go to E. I've got all the ones that go to F. That's every single diagonal in the entire polygon, and none of them contain exterior points. Okay, so this would be called convex because there aren't any diagonals that contain exterior points. So no diagonals contain exterior points. Okay, so this has 1, 2, 3, 4, 5, 6. This is a hexagon. Alright, so let's look at this sheet and let's look at each of these shapes and decide. Now they haven't marked them, but let's just visually say whether it looks like it's regular or irregular, as well as we'll count the number of sides and say what it is, and then also whether it is convex or concave. So this is 3 sides, so this is a triangle. Okay, and it appears that all of the sides and all of the angles are the same. So we would call this a regular triangle. Okay, and there aren't any diagonals because there are no non-consecutive vertices. Okay, so this would be called, this is just automatically, okay, convex. If there aren't any diagonals, they certainly can't contain exterior points. Okay, this one, definitely a triangle, but the sides certainly don't seem to be the same length. So this would be an irregular triangle. Okay, another word that we know for irregular, okay, they all look different. We could call it a scalene triangle because we learned that word. There's special words for triangles. Okay, and again is automatically convex. Okay, here this has 1, 2, 3, 4 sides, and they appear to all be exactly the same length, and they also appear to have exactly the same so it looks like it's equiangular as well, so we would call this regular quadrilateral. Okay, we know there's a special name for that, but for now we're just going to call it a regular quadrilateral. And then if I were to draw the diagonals, there would be this diagonal and this diagonal. There's only 2 of them in there, and neither of them contain exterior points, so this is convex. Okay, this one has 1, 2, 3, 4. Okay, definitely not all the same length, so this would be an irregular quadrilateral. Okay, again, only 2 diagonals, neither of them contain exterior points, so this one is convex. Okay, this one has 1, 2, 3, 4, 5 sides. They all appear to be the same length, and all of the angles appear to be the same as well. So this looks like a regular pentagon. And if I were to draw in the diagonals, hopefully you can see, no matter where you put them, this one is convex. No exterior points in those diagonals. Okay, this one also have 5 sides, but not the same length, so it's an irregular pentagon. And hopefully you can see that it is convex. This one has 1, 2, 3, 4, 5, 6 congruent sides, and the angles also look like they're congruent, so this is a regular hexagon. And it is convex. Can't draw any diagonals that contain exterior points. This has 1, 2, 3, 4, 5, 6 sides as well, but they're not the same length, and the angles certainly aren't the same, so this is an irregular hexagon. And this is the first time where we can draw a diagonal, and it definitely has a whole bunch of exterior points on it. So this one is concave because it has a diagonal with exterior points. This has 1, 2, 3, 4, 5, 6, 7 congruent sides and angles. So this is a regular heptagon, not sept, heptagon. Okay, hopefully you can see that we're never going to be able to draw a diagonal that contains exterior points, so that's convex. Okay, this one has 1, 2, 3, 4, 5, 6, 7 as well, but it's irregular heptagon. And you can see that there is a diagonal that contains exterior points, so this is concave. This looks to have 1, 2, 3, 4, 5, 6, 7, 8 congruent sides and angles. So this is a regular octagon. And it is convex. Can't find any diagonals that have exterior points. But this octagon definitely has a diagonal with exterior points, so this is a concave, irregular octagon. Okay, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. So, and the angles as well. This is a regular nonagon, and it's convex. This has 1, 2, 3, 4, 5, 6, 7, 8, 9 as well, but it's irregular. And definitely there's a diagonal here, another one over here. There's more than one diagonal, so this is definitely concave. It's got those diagonals that contain exterior points. And then we've got a regular decagon. This one is convex. And here we've got an irregular decagon. And this one has a diagonal there, a diagonal there, a diagonal there. There's lots of you can at least find those three. Probably even this one right here contains diagonal points. It has some diagonal points. Not all of them are diagonal, but some of them are. Okay, so there's lots of diagonals here that we can find that contain exterior points, so this is concave. Okay, so that is classifying convex and concave. And the last thing that we want to look at is something called interior and exterior angles in polygons. Okay. So we've got interior angles and we have exterior angles. Okay, so an interior angle is an angle formed by the sides of a polygon with a common vertex. Okay, so imagine here's your polygon. Okay, so I've got this side and this side right here, they share a common vertex. And the angle that they make, so in here, this angle right here, this would be an example of an interior angle. And that makes sense because it's on the inside. So this would be an interior angle, this one would be interior, this interior, this interior, and this interior. Okay, now exterior angle, you might be tempted to think is just the angle made by the sides on the outside, but that's not actually what it is. Okay, so the exterior angle is an angle formed by, so it's an angle formed by a side and an extension of an adjacent side. So let's look at what that means. So once again, let me draw. Okay, so here I have a side, and let me make the extension of an adjacent side. So I could take this adjacent side, and then I could extend it out this way. Okay, and then this angle out here made with the side itself and the extension of the adjacent side, this would be an exterior angle. Okay, so let's try another one. So let's say I've got, you know, this side right here, and I could extend this out this way, and this side right here would be an exterior angle. Okay, so it's made with the side and an extension of an adjacent side. So those are exterior angles. Okay. All right, so I think that's all the definitions that we need, and that should get you everything that you need to be able to finish the homework from lesson 15.